Hello friends, welcome to Truth of Physics. In this video, I will discuss on the Laplace's equations solution in spherical polar coordinate system with an example. That means I will discuss a problem which involves this process, the solution of Laplace's equation in spherical polar coordinate system. So, in the previous class, that is in the class number 1, lecture number 1, I have discussed the solution in plane polar coordinates, in our Cartesian coordinate system. Okay, so the link of the video I will give in the description box or in the I button. From there you can watch that video, and also the related topics, that is what is Laplace's equation. All the videos with these topics, these related topics, which will be very much helpful for you if you don't know from earlier, then I will give all the link of the videos, related videos, in the description box and also in the I button. So from there you can watch those videos also, and if you have any doubt then you can also comment me below, and if you are new then also subscribe this channel to get the notifications of my upcoming videos. So in our today's problem we are given, suppose this is a annular spherical spheres, okay, conducting sphere. The inner radius is Ra and the outer radius is Rb. Now the inner sphere is spherical shell, okay, this is basically the spherical shell, hollow. The inside is hollow, okay. Hollow means here one is confirm that hollow means here rho is equals to 0, and you can easily understand that we have to use the Laplace's equation here. Now what is the question, right? What is the question? The question is it is grounded, the inner shell is grounded and the outer shell is at V equals to V0 voltage. Now the question is we have to find the expression of V in between these two spherical shells, that is in this region, okay, in this region we have to find the expression of V. Number 1 question. And the number 2 question is we have to find the surface charge densities on both the two spherical shells. The induced surface charge density sigma is equals to what? Okay, so in a similar fashion like our previous class that I have discussed first, we again use the Laplace's equation. This is the form of Laplace's equation in spherical polar coordinate system. Okay, you can easily come to this result from the concept of curvilinear coordinate system. Okay, generalized form. First put the generalized form, that is 1 by h1 h2 h3 and all the things, and from there you can come to this. Okay, now you can understand that here the potential is varying only with radius, right? The potential is varying only with radius. That means this is a case of where the potential varies radially only, not with the angle theta and phi. Okay, you can understand how. You can see that for the outer shell, V is all over this sphere. That means when we this is fixed, Rv is fixed, okay, Rv is fixed, the radius is fixed, outer radius, and I am just rotating this. I am suppose I am here, okay, I am here and I am just moving along this path, and in all the path the potential V is same. That means the potential is not changing with the change of theta. This is what theta, I am moving, that means the theta is changing, but with the change of theta the potential on the surface is not changing. That means the potential, and similarly for this small sphere you can easily understand that. So but the potential is changing where when we small down the radius from Rb to Ra, then the potential potential vanishes to 0 as this is grounded. That means the potential is varying only with radius. That means here inside any region with the distance, varying distance, the potential will be different for different coordinate of R. For different values of radial distances, the potential will be different. Now we have to find that relation, how the potential will be potential vary with the radial distance. Now so you can understand that this is not changing with the theta. That means these derivatives and these derivatives will be 0. So this is also 0 and this is also 0. But remember this whole form, This will help you immensely in your problems, in solving your problems in many situations, in many parts of physics. Now only this part will become 0. That means only 1 by r square del v over del r square del v del r is equals to 0. That means this will be equal to 0, right? That means this will be a constant if we integrate this, and so if we take this r square to here, this will be r square and this will also vanish, right? And now v will be equals to minus c over r plus d. Another constant, c and d are integration constants. Now we can find the integration constants with the given boundary conditions. Number one boundary condition is at r equals to ra. What happens? This v becomes 0 at r equals to ra. So okay, I am writing here at r equals to ra, v is equals to 0. So d becomes c over ra, right? And at r equals to, okay, so I am putting this here. So v becomes minus c over r plus c over ra, right? Now putting the another condition, v naught, v is equals to v naught at minus c over rv plus c over r, right? So the c becomes v naught divided by 1 by ra minus 1 by rv, right? So this expression, what will be this expression? 1 by ra minus 1 by r into c, that means v naught over 1 by ra minus 1 by rv, right? Calculating this, you will come to this result. Okay, now with this you can find this sigma. How? Using the boundary condition. I am showing you how you can solve this for the outer surface, and you have to do what? You have to do that for the inner surface. Very easy. Okay, very easy. So watch this minutely. You can do yourself for the inner. Okay, so for the outer, rb is the radius, right? So what is the concept? The concept is using electrostatic boundary condition for this surface, the outside surface. What will be that? The electrostatic boundary condition, I have already made a video on the electrostatic boundary condition, and the link of the video I will give in the description box. So what says the electrostatic boundary condition? That says that E above perpendicular minus E below perpendicular is equals to sigma over epsilon naught, where sigma is what? Sigma is the surface charge density on the surface. This surface, on this surface, the surface charge density is suppose sigma. So this is the case. Now E is equals to what? Minus del V del X, or simply minus grad of V. So here, as this is varying with only radius, so I am considering only minus del V over del R, right? Here R is the variable. So E above, there will be minus del V over del R above. So, and there also a negative sign, minus del V over del R below. So an additional negative term is coming, right? So I am just putting the negative term in the right hand side. Then what happens? Then this equation, okay, this equation becomes what? Then actually I have a shortage of place here to write. So I am removing this thing, okay. This will become what? Minus del V over, okay, minus I have taken outside, and minus will be minus I have given in the right hand side. So what will be this? Del V over del R above minus del V over del R below, and that is equals to minus sigma over epsilon naught. Now del V over del R above, we have to derivative it. This is the expression of V in between the region. So we have to derivative it. This term will also, this term will be vanished because all the things are constant here. This we have to, the variable is only here in the second term, and minus 1 by r, the derivative of this, what will be that? R to the power minus 1 means 1 by r square, right? So 1 by r square v naught Ra Rv by r square Rv minus r. Now this term del v over okay, one more thing, I have done a mistake, that is that the above region, in the above region the electric field will vanish. In the above region, this region, the electric field above will be equal to 0. Why? That is a long explanation. So later in any video I will discuss that. Okay, so here this will be 0, and the E below, we can find the E below, that is in this annular region. So what will be that E below? The E below will be this, the derivative of this, and after derivating we have to put okay, the derivative of this, that means this is going to 0, and we have to and this is, and there is a negative sign, so this will be equals to minus sigma over epsilon naught, and these negative signs will be cancelled out. Now the final expression will be this. Now from here you can find easily the value of sigma, and this sigma is what? The sigma at the outer surface, that is at r equals to Rv, at r equals to Rv. Now that thing that at r equals to Rv, you have to put the value of Rv here. Here you have to put the value of Rv because you are finding the sigma in the distance what? Rv. So just put down this relation, and put the value of Rb in the place of r. So this is the expression of the surface charge density of the outer shell. So I think that you have enjoyed and understand also the concepts and how can you solve this type of problems using the Laplace's equation. So for next videos you have to subscribe this channel and hit the bell icon, and take care of yourself. Thank you for watching.